For the next segment, we're going to talk about a few of the research projects that have been simulated, and I'd like to turn it over to Martin Lostra, a postdoc at Berkeley, who will be taking over as the master of ceremonies and giving me a break. Thank you, Martin.
Excellent. Thank you, Edward. I'm sure you're happy to take a break. Okay, so let me share this slide. So as I was doing my PhD as a graduate student, coinciding with, I guess, the first year of this project, I spent most of my time trying to convince myself that the reactor model made sense, and then I spent a lot of time trying to convince others that it made sense. And it's a little difficult to do that without having actually built any artifacts, haven't done any engineering, without any proof of concept. So we started building things, and as more people bought into the idea, we got a much larger group of people that has been growing ever since, that have been actively contributing to this project. And at this point, it's actually become kind of overwhelming how much activity there is. So I just sat down and tried to kind of create a map of all the things that are currently going on in the project. And we won't be able to discuss them all during this session. But I would like to highlight some of them. So obviously there's a lot of engineering that goes into the compiler, and we have found that the research problems kind of find you as soon as you start building things. There's also been a very perhaps surprising synergy with the theoretical aspect of this work, where some of the primitives that we built into the language and that are key in the reactor model have been instrumental in developing some new theory. Specifically, it's allowed us to generalize and quantify the famous cap theorem that's due to Eric Brewer. That's some very recent work. We have also a lot of activity, keeping up with features that we want to see implemented in our runtimes, right? So each target language has its own runtime, and there are people actively working on those, keeping them in compliance. And that's a huge engineering effort. One recent thing that I think is interesting mentioning is, now that we have a federated execution capability and we have this way of reasoning about trade-offs between availability and consistency, it will be interesting to conduct experiments where we essentially do chaos engineering on our running programs to validate some of those ideas. Also, tooling, super important. I'm just very thankful that we were able to pull off, having a working IDE just a few hours before we had this tutorial. It's a lot of work that goes into this, and I'm very thankful for all the support from everyone on the team in getting this ready. Exciting new developments. Support for other editors than our Epoch IDE. I think that that will really be important in engaging more people in the community. We haven't talked that much about applications. Some of the talks in this session will compensate for that. And lastly, platforms. Well, since we now have a programming language that has time in it as a first-class citizen, it provides a whole new view on how to deal with real-time problems, specifically with hardware support that is much better at fulfilling what programs with timing constraints in them demand of the hardware. So that's also an interesting topic that we'll discuss. So we won't get into all of these, but the ones that are highlighted here we'll get to discuss during this this session. So because we won't get to everything and everyone, I would want to briefly highlight the folks that are involved in this effort, some of whom you've already heard. They spoke during this tutorial. Other ones you haven't heard of. Recent collaboration with Julien De Antoni from INRIA has been very interesting, where we've been trying to focus on expanding tooling in the IDE, supported by a formal framework that he developed. We've seen the diagrams. That has been a huge feature for us. Reinhard from Hangsleiden's group has been on this, and Alexander Schultz-Rosengarten has been the key developer behind it. Sarouche, who has been featured in several of our segments during this tutorial, has been a very, very active developer, and involved in several different research directions. And then Theo Dresden folks have been really instrumental in all the work that we do in our compiler. I also wanted to mention Martin Schuberl, who helped us get Lingua Franca working on a bare iron platform called Patmos. So I would like to introduce to you now Christian Menard, who has already been featured in several of our segments, who is at TU Dresden, and he will talk a little bit about an effort that he led in achieving determinism in AUTOSAR. So I'll stop sharing. Christian, take it away.
Yeah, all right. So this is actually about not so much about ongoing research, but mostly about past research, and actually the research I did, and that brought me to that group and to the team, and to get hooked to Lingua Franca. So I looked into AUTOSAR, and for those that don't know AUTOSAR, so it's a worldwide consortium, an industry consortium, and it defines a standard, and they aim at creating a unified software for automotive applications. And this comes in two flavors. There's the so-called classic platform, which is focused on real-time applications, very constrained hardware, like small ECUs, microcontrollers, basically. And there's the newer adaptive platform, which is focused on very computational intensive applications. So high-level algorithms, autonomous driving, computer vision, these kind of things. And so this focuses on the adaptive platform. And the adaptive platform basically implements a service-oriented architecture. So you can define services, and clients can request these services, and then magically the two find each other via these middlewares. A common one is some IP. So all this communication is nicely hidden away. As a client, you just say, well, I want to talk to a server that provides the service, and then you can invoke methods on the service or subscribe to events of that service. Now, this brings some problems, actually. So service-oriented architectures are inherently non-deterministic. And to illustrate that, actually, we created a simple example. So this is a bit simplified, but this is most of the client code here. And what this does is, well, first of all, it requests a proxy to the service, so it connects to it and can send then stuff to the service. And what it does is just set the value, basically initialize the state of the service to 1, add a value of 2, and then retrieve the result. Nothing very complicated. Now, obviously, we would expect the result of this program to be 3, but it isn't, because AUTOSAR doesn't make any guarantees about the order in which these method calls are processed. They're actually all processed asynchronously. They might be processed in any order, and what we get is a distribution of possible results. So 3 is still quite likely, but it's only at 40%. And depending on the precise order at which events executed or these methods executed, you might get any results. Now you could say, well, this program is obviously broken because it doesn't synchronize properly. Yes, if we could use some mechanisms AUTOSAR provides to built-in synchronization to wait for the result, for the call to complete before invoking the next call. And yeah, we can fix the program in that way. But basically our argument here is that this becomes very tedious, and it's really, really easy to make mistakes for larger, bigger programs. And actually, this is nicely illustrated by the adaptive platform demonstrator that shipped alongside like the AUTOSAR distribution. So this demonstrator implements an emergency brake assistant. It consists of a few components. So there's a video provider, like let's say a camera, and then there's a preprocessor that does some filtering on the data and actually detects the lane already. So it sees where's the lane and which lane we're driving on. And then there's a computer vision component that sees what kind of obstacles are there and decides whether they are on the lane or not. And this then basically sends a list of the obstacles to the emergency brake assistant that makes a decision, is there a situation where I need to brake or not? Now, obviously, we want this to work correctly, and we don't want any weird timing errors in this kind of program because it's really, really critical. Well, there are plenty of those timing errors in this demonstrator, actually, as we found. So I don't want to go into the details of the precise nature of these errors right now. Just to give you an idea, this is an experiment I did where I run this demonstrator 20 times after one another, and I just measured how often these different kind of errors occur. And interestingly, for some of those runs, everything is more or less fine, barely any errors, but there are a few occasions where it's really above 20% of errors. And that's quite interesting because apparently not only is this program non-deterministic and has errors, also the error rate is non-deterministic, and it really depends on how all these different components come up and the timing of those. Now, in order to fix this, what we did is introduce a framework that basically is intended to bring vectors, the vector model to adaptive AUTOSAR. And as I said earlier, this happened before Lingua Franca, before we got into the project. But this is basically using a standalone vector library. And yeah, the basic idea was to just grab the logic of each of the different components, interactors, and then have some transaction going on. I'm also not going into the details of this, that uses the AUTOSAR utilities to still send messages back and forth. And yeah, so what's left for ongoing research in this is actually to integrate this back now with Lingua Franca. And what I would like to do is to be able to generate AUTOSAR compatible code directly out of Lingua Franca programs. And it would also be interesting to integrate that with other automotive frameworks like ROS and Autoware, which I believe you will hear about in the next talk. So that's it for me.
All right, thank you, Christian. So even though Christian and I have been working closely together since 2019, the funny thing is that we actually still haven't met physically. One time I came very close. I was on my way to a conference in France, and actually we both were, but that conference got canceled. And I spent literally 3 hours in the Charles de Gaulle airport after I had to return because otherwise I wouldn't be able to get back into the country. We're still looking forward to that meeting. So the next person that I'm introducing is Soroush Bateni. I had the pleasure of actually meeting him this summer. He visited Berkeley. We've been working with Soroush since 2020, well over a year, and it was a pleasure to finally hang out and work together on this Autoware project that he will present now.
Thank you, Martin. Okay, so I will just use the 10 minutes that I have to briefly discuss an overview of automotive related research that I've been involved with. And just as a precursor, I want to give a motivation behind that research, which is an observation that modern automotive systems are becoming increasingly reliant on sophisticated distributed architectures. They make use of AI, parallelism, and accelerators such as GPU. But more importantly, as an overall theme, all modern autonomous driving systems will benefit from two key properties. So one of them is testability, and the other would be that these systems should at all times have a consistent view of the state of their environment. And to just give a little bit of a more in-depth definition for what I mean by testability and this consistency, the testability, the way we define it is given an initial state and a set of inputs, there can only be one correct behavior. Now, the way you define behavior is really model dependent, application dependent. In this specific case, what I mean is that if you present a system with a test vector, you will always get the same output no matter how many times you execute your program. This is, of course, not exhaustive. You can't produce all the possible test vectors, but it is nonetheless a method that is heavily relied upon in the industry. The other would be that these systems should always have a consistent global view of the environment, which means that all the components should at all times be in agreement about not only the state of the environment, but how we got there, right? The order in which states has been changed in the environment that got us to our current state. And then if you have that, then detecting race conditions and causality loops and so on are very easy. And you saw sneak peeks of this using our tooling in earlier demos. So I have here two examples that we've used in our research extensively. One of them is Autoware Auto, which is the second version of Autoware. They, back in April, had their 1.0 release, which was an autonomous valet parking. You can see here. So you can essentially, this is running a simulator, although they've also demonstrated it using a real vehicle. This is the LG SVL simulator, by the way. You can see that we, in this demo, we can drop the vehicle at any point in the parking lot and then point it to a drop-off zone, and the vehicle is capable of driving itself and parking there. Okay, so we took this example and we looked at the architecture of it, which is quite complex. And then we asked ourselves those two same questions. Is this architecture testable? And does it always present a consistent view of the environment? So I won't go into details about all of these individual nodes. I just want to focus on two very simple, relatively simple nodes. So here I have the LG SVL interface, which is the interface node to the vehicle, and the behavior planner, which is generally the brain of the operation. The behavior planner is the one that tells the vehicle overall where to go. So it assigns trajectory. And you can see that the interaction that I'm showing here is that the LG SVL sends two things to the behavior planner. One is the state report, which reports the state of the gear, including also other things. But the main thing that I want you to focus on is that this state report contains the gear information. So is the vehicle in forward gear or in reverse gear? And then it also sends a vehicle kinematic state, which is the reports include, among other things, reports the velocity of the vehicle. Okay, so is this architecture testable? So in order to understand the answer to that question, we have to look at the underlying framework, which is in this case, Robot Operating System version 2. And what guarantees does ROS actually provide. In this case, it only provides the following guarantee. So you have point-to-point in-order delivery of messages. And you can demonstrate that by running a simple test. So imagine that the LGSVL interface produces a forward gear on the state report, and then later on produces a reverse gear, again on the state report. So what would the behavior planner see? Because of the guarantees provided in ROS, the behavior planner will also always see that the vehicle has been in forward gear, and then later it has switched to a reverse gear. So in that case, the system is both testable and presents a consistent view of the gear, because the behavior planner will always be in agreement with the LGSVL interface in the order in which gear changes has occurred. So both of them will agree that the vehicle has been in forward gear and then later has switched to a reverse gear. Okay, so in this case, ROS provides both testability and consistency. However, let's look at a more sophisticated test. And this test is as follows. So the LGSVL interface produces a state report, which contains the forward gear. Then it will produce a kinematic state. Because the vehicle is in forward gear, it will have a positive velocity. Then it will produce a reverse gear. And because then the vehicle is in reverse, it will produce a kinematic state with negative velocity. Okay, and now what does the behavior planner see? So the expected thing that it would see is it would see them all in order. So it would see that the vehicle has been in forward gear with a positive velocity, and then later it has changed to a reverse gear with negative velocity. However, what we actually see is when we ran this test for 300,000 times with varying periods of running this test, we saw that, and this is the important thing, among 300,000 tests, only about 0.2% of the time we saw that the behavior planner is not seeing the behavior as expected. So this is quite dangerous, because if you run this test even 100,000 times, you will not see any errors. So then you can come away thinking that your system is testable. And you can think that the behavior planner will always consistently understand what's going on with the vehicle. However, if you run it for 300,000 times, you will see a dangerous sequence like this, which is, so steps 1 and 2 has been seen by the behavior planner. So at the step 2, the behavior planner would think that the vehicle is in forward gear and it has a positive velocity, but then it sees 4. So now it sees that the vehicle has a negative velocity without being in the reverse gear, right? So how would the behavior planner interpret this? Is this because of an accident, that the vehicle has been impacted so hard that it's now moving backwards? Is it because of a component failure, or is it just because ROS has introduced an error? And the behavior planner really has no way of knowing this. And we have quite a few examples of this. I just included the simplest one. But the bottom line is, what we ended up doing was we actually ported this Autoware Auto 1.0 completely to Lingua Franca. You can see it here. And it interacts with the LGSVL interface, although this is still a work in progress. There are some aspects of it that still require debugging, but we have extensive results that show that this port has been effective. So just to demonstrate one is, so the overall takeaways has been that this port of Lingua Franca using the centralized coordinator will have 0 errors, essentially. So the error rate will go down to 0. However, there is a drawback with our centralized coordinator, which is that because it's loosely based on HLA, a simple network partitioning will just stall the execution. For our decentralized coordination, we have a more interesting trade-off, which is that the safe to process offset that we talked about in the tutorial, you can actually play with it and change it. And you can see in this graph that the maximum theoretical STP offset for the example that we just saw is 24 seconds, which is too high. However, if you set your STP offset lower, the strength of Lingua Franca is that if that STP offset is violated, then you can detect that, whereas you can't detect that in ROS. So if your messages are late, as we saw in the tutorial, your STP handler will be invoked, and then you can handle that error. The other thing that I want to demonstrate is another automotive related application. This was raised by our industry partner, Ravi Akella. And this was about an intelligent intersection where you can see that there are 4 vehicles here that want to enter this intersection, and they need to coordinate so that they don't have an accident, to put it bluntly. And really, there are 2 ways of coordinating this. One is you can have a roadside unit that coordinates their entrance. That's not as easy as it sounds, but the more complicated solution would be to have these vehicles coordinate in a P2P fashion, and that is also ongoing research. But the thing that I want to show is that we actually implemented this intelligent intersection using another prominent vehicle simulator, Carla. You can see the demo here. So the structure of the demo, that in this case, we have 4 vehicles, and which represent the vehicle controllers and so on. We have a roadside unit, and we have our Carla interface, which in a real application would be replaced with an actual vehicle interface, just like Autoware. And we actually have a demo of this on YouTube with, it's not switching to the, okay. So you can actually try this. This is on our Lingua Franca repo. It's called Carla intersection.lf. It's under experimental. And you can see that I'm just running the generated PI file, which will in turn run this. And if you have Carla installed, we can play with this. We can change the vehicle controllers, the RSU, and so on. And you can see that the vehicles are coordinating their entrance to the intersection. And there are a lot of interesting trade-offs involved here, but I guess we don't have time to go over them. But feel free to refer to the quantifying cap paper that Martin pointed to. And with that, back to Martin.
Thank you, Sarush. This is really extremely cool work, and I'm really looking forward to see Lingua Franca have an impact in the automotive community. So after Sarush, the next person I will be introducing is Efsane Soyer. She is a junior in computer science at Berkeley, and she did a terrific job presenting her work in progress that she has been doing together with Xiaokai Lin, one of our graduate students, at the recent NSF CPI CPSPI meeting, and she will present part of that presentation right now. Efsane, take it away.
Thanks, Martin. Let me share my screen. I guess you can now see my screen. Okay, perfect. Hello, everyone. So we also want to include the notion of time, we kind of talking about it at every layer of abstraction instead of hiding that from the designer. So we're proposing an engineering paradigm where timing semantics is baked into every layer of abstraction, from the microarchitectures to the model of computation. And at the level of microarchitecture, we propose combining Lingua Franca with PRED machines, which are processor architectures that are capable of precise timing. So our goal in the PRED project is to demonstrate that you can achieve excellent performance while still having control over timing at the microarchitecture level. And we have demonstrated that timing predictability and repeatability can exist in parallel with performance. Like as of now, 3 generations of PRED machines have been developed, and FlexPRED, the latest version of the PRED machines, is a fine-grained multi-threaded RISC-V processor designed specifically for mixed criticality for real-time embedded systems. So in other words, FlexPRED offers a configurable architecture that can handle both real-time functions with repeatable timing and non-real time, but performance sensitive applications. So we are currently working on bridging the gap between Lingua Franca, the deterministic programming model, and the Pred machines, the processor architecture that are timing predictable and repeatable. And in order to make these timing-aware layers of abstraction work, we are making progress towards running Lingua Franca on FlexPreg architecture. On top of that, as you all know, embedded system constitutes a major part of CPS applications, and we are working on adapting LF on various other embedded platforms as well. We are currently supporting Rocket Core and Spike platforms and developing the Arduino this semester along with the Pressbreath. So right now, I would like to show you a quick demo and some additional supports that are needed to support this bare iron platform. So here we have, sorry, I'm really bad at typing and speaking at the same time. So here we have an LF program for a robot that has sensors, a controller, and motors. So we have been saying how we can run this program in various platforms, but how can we actually run them? What supports do we need if we want to run it on a bare iron platform? So if we go into So one argument that we have been talking about is the idea of the physical time. And normally the way we support this is using the OS features, OS tools. However, in a bare iron platform, we kind of need to get the current physical time by another methodology. And the way we implement it is that like by counting the cycles, we are getting the notion of this physical time. So this is one of the additional supports that we give here. And the other one is this return, this custom return function in order to terminate this spike simulator. And lastly, we have this SBRK implementation here to enable memory allocation in bare iron platforms. The one thing that is worth emphasizing here is that just by implementing a couple extra services, we were able to make LF runtime work in a bare iron environment. And like, run this program now. Here. If we run this program, we see that the program terminates with an emergency stop because the deadline is missed. And this is because we have a deadline specified in our LF program for both our controllers and sensors, and which is a really good practice when it comes to real-time systems. But since Spike is not an actual architecture, we kind of make assumptions here before we run, including the assumption for clock frequency of the Spike. And when the clock frequency and the deadline value, they both determine whether or not we are missing this deadline. So if we want to avoid missing this deadline, we either need to increase the value of our deadline, which is not always possible depending on the application, or increase the assumed clock frequency. So I guess that would conclude my presentation. Thank you.
Cool. Thank you, Afsane. This is excellent work. I always like to think of this project as kind of a moonshot project that is turtles all the way down, so to speak, where we have time at the programming level and all the way down to the logic. Really nice. Okay, going to the next speaker, Alexander Schultz-Rosengarten from Kiel University, who has already presented several segments in this tutorial. He brought to the table the idea to augment lingua franca with modal models. A new syntax, new diagrams, and this is a work in progress. I really see this as a really interesting cross-fertilization between lingua franca and the sequential state charts that his group is working on. All right, please go ahead.
Thank you, Martin. Yeah, most complicated systems usually work in some kind of mode. So they have different modes of operations. And the idea of modal models really is to express these modes in some high-level fashion. And usually this is done by some form of finite state machine or state charts dialect. And here for lingua franca, the idea is to create modal reactors. And they should not be too intrusive into the syntax. So they should come in as a lightweight layer on top of the current structure of reactors and reactions, and especially don't hinder the form of polyglot nature. This is essential to the lingua franca languages. And in order to fill the gap to the classical visualizations of state machines, here again the diagrams play an important role. And on my screen you can see an example. This is inspired by the steam boiler specification problem by Jean-Raymond Abrial. The steam boiler here has a few sensors, computes the water level, and by that controls the boiler. And if I look into the water level here, you can see that the computation is depending on the mode of operation here. And if we look into the normal mode, you can see that there are two reactions in it. And that's essentially it. The modes encapsulate the contents of a reactor. And the code generation then will handle the activation and deactivation of these timers, reactions, and so on, so that only those in the active mode will be triggered and can run. And here in the normal mode, the water level is computed based on the sensor, and there's another reaction here that can actually switch the mode. So here in the effects, other modes are declared that allow us to draw these diagrams, and the actual mode switch is done in the target code, same as setting an output. This will change the mode of operation. And if the water sensor fails, it will switch to a rescue mode if there are flow sensors available. If these also fail, well, it has to enter the emergency mode and the entire plant needs to be shut down. And these modes can be composed differently. So if you look at another example, you can see here a reactor with two modes, one converting, one discarding. And in the conversion mode, you can see a converter that has uppercase and lowercase. And what this program does is it takes a string, character by character, and either discards characters or processes them by converting them to upper or lowercase. And I can quickly run it. And you can see this one switches between discarding characters, converting them to uppercase or keeping them lowercase. And what's maybe interesting here is we also have different ways of entering modes, because you can decide if you left the mode and then re-enter it, you can decide if it should continue as before or it should be reset. And in this case, it continues. So even after switching to lowercase and activating the discarding mode, when it re-enters converting, it will still convert to lowercase and will not switch back to the initial configuration of converting it to uppercase. And these give the opportunity to the modeler to express such modes in lingua franca programs, but also give new ways of performing static analysis or model checking on the program that involves the modes of operation. And these will be part of lingua franca in the future. Thank you.
All right, thank you, Alex. I think that this will be a very powerful extension of lingua franca. This is very neat. So next up is Xiaokai Lin. I would like to briefly mention that so Xiaokai is a second-year graduate student in our group, and at some point he asked, so could we maybe get some undergraduate students to work with us in the group? And I said, I don't know, how do we do that? And so he organized a recruiting effort, and that has led to about a dozen undergraduate students being now engaged in work related to lingua franca. And he's been helping advise many of these groups. And now he will talk about his own research, which is automated verification. He's interested in verifying safety properties of lingua franca programs. Xiaokai, please take it away.
Okay, thank you very much, Martin, for the very kind introduction. So hello, everybody. I'm very excited to present the current work on leveraging formal methods to verify lingua franca programs. So cyber-physical systems tend to be safety critical, and often we don't just want to rely on testing, but also want to obtain formal guarantees about the correctness of the system. So in this demo, I'm going to show you how we can leverage the semantics of lingua franca and the current state-of-the-art SMT solvers to automatically verify some of the safety properties that developers might have when they build their system. So, right now, are you able to see my intersection example?
Yes.
Okay. So what you see here is a implementation of the centralized intersection application. This is similar to the prior demo that's shown by Salush, where connected vehicles try to enter the intersection autonomously without human intervention. And here you can see that the intersection is being managed by this RSU reactor, which stands for roadside unit. And there are currently two vehicles here communicating with the roadside unit. And the roadside unit essentially directs the vehicles and tell them, which one to enter this time, which one, to wait for a minute and then enter in the future. And what we're interested in, for this application is to see whether the behavior of this particular program allows for scenarios that are potentially dangerous. For example, could this program possibly allow for the scenario where both vehicles simultaneously occupy the same intersection, in which a potential collision could result? So let's try to check that using SMT. So here I have encoded the semantics of the lingua franca program, the application of the intersection, as well as the safety property, which is the mutual exclusion property, into a formal modeling language called Euclid 5. And here you can see that using Euclid 5 language, we have modeled the timing semantics in lingua franca. We're also modeling the reactions and the connectivity information in the intersection application. We have modeled the semantics of a trace, modeled the semantics of the happen before relation in reactors. And we further model the topology of the application, as well as what individual language, LF language component means formally. And lastly, here is where we detail all the semantics of the reactors. For example, events must be timestamped, and then they are processed in timestamp order, etc. And all of these are written in first order logic. And so here we construct our safety property. In this case, it's mutual exclusion. It is originally written in linear temporal logic, and here we transpile the LTL property into first order logic property. And then when we run our program using the Euclid 5 2-chain, we get an output like this. And you can see that the SMT solver has successfully found a counterexample that will lead to this particular unsafe scenario where two cars occupy the intersection at the same time. And the idea here is that the developer can manually go through the trace and try to recreate the behavior of the lingua franca program, and this can help them identify the potential bug in the program. And this will be an iterative process. When the solver no longer finds a trace that can lead to this scenario, we would say that this program is safe and basically satisfies satisfies the mutual exclusion property. Okay, so this is the current status of the automated verification effort. We are currently working on automatically generate this formal model, formal Euclid model directly from lingua franca programs, because most of the information can in fact be derived from the coordination layer alone. We actually don't even need to look into the target code. So this will also be a target independent feature. And we're also working on making the proofs compositional so that we'll be able to construct proofs incrementally for larger systems. Okay, thank you very much for your attention. And this concludes my demo.
Very cool. Thank you, Xiaokai. I should also mention that it shouldn't come as a surprise that Xiaokai is our formal verification guy, since he's also co-advised by Sanjit Seshia. Up next is Hokan Kim. Hokan used to be a fellow graduate student. We were both graduate students in the same group, with Edward being our advisor. He moved into industry. He worked for Google for a number of years, and he was very recently hired as a professor at Hanyang University. Hokan has recently gotten involved into several sub-projects. He's been helping out with the federated execution in the TypeScript target, and he actually rewrote the code generator in Kotlin, or TypeScript code generator in Kotlin, so he hit the ground running. His focus of his PhD work was on security, and we're very much interested in leveraging his knowledge about security. So he will talk a little bit about what he plans to do in the context of lingua franca when it comes to security. Hokan, please go ahead.
Thank you, Martin, for the kind introduction. I'll be discussing ongoing research on how to secure communication for federated execution in lingua franca. Currently, in lingua franca, we assume that the RTI, the runtime infrastructure, and all federates run under a trusted environment without any adversaries. Thus, all network messages are sent in plain text without any protection, such as message authentication or encryption. However, this becomes a considerable challenge when this assumption is not true. For example, when we run LF Federation communicating over the internet, or on an open network. In such cases, the Federation will be vulnerable to various attacks, including maliciously altered messages that can run malware on federates when they are deserialized, or sensitive information being leaked to attackers. Here's an example attack scenario where the attacker joins a federation with a malicious federate. The RTI authenticates each federate using a unique identifier called Federation ID, which is also sent in plain text. The attacker can simply eavesdrop on the Federation ID and present it to the RTI to join the Federation in place of a valid federate as shown here. One may think we can apply conventional security solutions such as SSL TLS or Kerberos to address this problem. These conventional solutions have been widely used and very successful for the web. However, they require digital certificates or standard security measures, which may not be a proper option for resource-constrained devices. Challenges arise when we try to apply these solutions to Lingua Franca's federated execution. This is because not all federates can afford the security overhead due to the additional network payload or heavy computation. And the distribution of secrets is a non-trivial problem since there is no established way of building trust among these devices. Also, the support for the distributed communication is limited for these solutions. To address these challenges in securing communication for the LF Federation, we are using SST, Secure Swarm Toolkit, an open source software toolkit for authentication and authorization of the IoT using edge computing. This is also my PhD thesis work. And the main component of SST is called Auth. Auth is a locally centralized, globally distributed software entity for key distribution for security services such as authentication and authorization. SST provides knobs to configure options between stronger security guarantees and less overheads, including communication or computation overheads and energy consumption. Therefore, SST can provide security solutions for federates that cannot afford conventional security measures. A remaining challenge would be how to find optimal configurations for given applications and platforms running the LF Federation. The work-in-progress design of integrating SST with federated LF is as follows. The auth plays a role as a key distribution center among the RTI and federates in Lingua Franca. The security configurations are going to be generated as part of the code generation and distribution of an LF federation. These code generation and distribution processes will include the initial setup of SST and the auth, specifically the key distribution mechanisms, communication policies, and secret keys. We are currently focusing on the centralized execution of LF as it is more aligned with the SST's architecture, but we believe that this can be easily extended to the decentralized execution. Okay, this ends my presentation. Thank you, and back to Martin.
All right, thank you, Håkan. SST seems like a really perfect fit for Lingua Franca since Lingua Franca targets both small embedded systems for which that resource consumption versus security trade-off is really important, but also large-scale distributed systems. So yeah, this looks very promising. Okay, last but not least, I would like to introduce Peter Donovan. Peter Donovan is one of the undergraduate students that we recruited earlier this summer. Peter is a rising sophomore, and I've been really impressed with his work. He has basically single-handedly built a Visual Studio Code extension with lots of features built on top of the language server that gets generated as part of our compilation process that Xtext provides. And so there is already a basic version that we will probably publish soon based on this work, and that would bring really nice lingua franca features to the VS Code editor. So Peter, please go ahead.
So the nice thing about using the language server is that it allows us to use the language server protocol, which is a standard for communications over JSON RPC between the language server and the editor. And so that allows one language server to be reused across many different editors that also follow the protocol with very little additional code. Right now, we're working on compatibility with VS Code, but of course, we would like to support your favorite text editor, whatever that is, and hope that it will allow a lot of code reuse. So the editor sends information about lingua franca source files to the LF language server, which is a jar, and the language server does lingua franca syntax validation, and it does any analyses that the user requests. And it also can use the generated source code as input to target language tooling that, like, you might be familiar with, like formatters and linters. And then it sends the results of lingua franca specific analyses and target language specific analyses, both back to the editor as appropriate. So here's yes. Okay, so here's the smokers example that Christian mentioned earlier. The example of a program that is implemented a lot more elegantly, that really benefits from the lingua franca syntax. So as you can see, diagrams are available in VS Code because of this extension as a result of Alexander's work. The language extension also obviously detects lingua franca syntax errors. So here it reports that I inserted a typo and now the main reactor doesn't have a name that matches the file name. And it also validates it validates target language code. So if I insert a syntax error into this reaction body, then there's a little bit more of a delay. There are certain optimizations in the code generator that haven't been implemented yet, like it doesn't cache previously generated models in its correspondence with the generated code, but it does report a meaningful error message and in the right place for the user. Of course, the language extension or the language server also provides the same basic features that are available in Epic IDE, such as go-to references. Okay, that concludes the extension.
All right, perfect. Thank you, Peter. Yes, this VS Code plugin, I think, will be quite instrumental in getting a broader community engagement. It's not just a language server, it's a language and diagram server, as it's currently called in our code base. And Alexander Schultz-Rosengarten and several of his colleagues have worked hard to get the diagram part working, which we're also very thankful for, that's now available in VS Code, because without it, that would really have crippled the user experience. All right, with that, I will hand it back over to Edward for concluding remarks.
What I'd like to do now is just conclude with, I think, what is hopefully obvious for those of you who have been persistent enough to stick through all of this. This is an incredibly exciting project with a lot of potential and an extremely talented group of people that I am just thrilled to work with. I, like Martin, am looking forward to meeting some of them physically in person. It's kind of remarkable how this pandemic has led us to actually work very closely with people for years now without ever having physically met. It's a very curious situation that I've never experienced before in my life. But in any case, I'm really enjoying working with this team. And with that, I will stop the recording and hang around for any questions that might come up.